peoples on whose traditional territories the University of Victoria stands, and the song He's Esquimalt with Saunders peoples whose relationships with the land continue to this day. So I think we'll see some people pop up, I'm sure, as we go along, and I think most people probably know who you are, but quick overview. I won't try and cover what you're going to talk about, of course, Rodney. It looks very interesting. But Rodney Herring is a professor, of course, in mechanical engineering, and has an interesting background. At least when I first met you, you were doing some interesting space-related work, and your breadth of research seems to have evolved from the nano to the macro based on what I see in your abstract with the ionosphere. So it sounds like a very interesting array of topics. And so at the end, what we'll do is we'll see how we're making for time, but I'll try and moderate a bit of the questions if it's needed. So over to you, Rodney.
Okay, I'll just share my screen. Is that good?
Yep.
So actually, I contacted Andrew about a year ago. I wanted to meet UVIC members because many of my research projects involve energy and power and stuff like that in many kinds of forms. So, and I really didn't know, I've never really been connected with UVIC throughout my time at UVIC. So I was curious. And so what I'm going to talk about is about imaging systems. I'll give a very brief personal introduction, but I think Andrew did a pretty good job. But also I'll talk about these crystals, what I'm using to clean wastewater and generating power, and how in the end, I think we can just receive the wastewater, and what we get out of it is so valuable that we can clean for free. Anyway, and then I'm going to talk about a radio wave imager of the Earth's atmosphere and ionosphere, and some funding opportunities. I want to talk about collaboration with UVIC, or even being an UVIC member, and wrap it up. So what I base my imaging systems on is the wave equation, and any kind of intensity we see in the image is proportional to its amplitude and the phase information. My imaging systems have a very common theme. I don't care about the amplitude, although it carries the phase. So I only need like one photon or one photon. As long as it brings me this phase and I measure it, I don't have to measure it a second time. This is hugely different than almost all the other imaging systems that people are making today or providing. So why is a phase so interesting? Well, it gives us information, physical information about the object that we're imaging, such as its temperature, pressure, composition, power, energy, wave vectors, strain, you name it. So the phase information is extremely valuable to me. And as a result, I find that these are my imaging systems, and they're all going very well, all very positively, except for one that doesn't exist anymore. But it sees, in my lab have a Mossbauer spectrometer, and it sees right down to the neutrons and protons. I mainly use it for looking at iron, because iron is everywhere. And you'll see in my research, I use iron. It's a very special type of atom or ion. Most people know me for my scanning transmission electron holography microscope, which has a very high resolution and sees down to about 1/10 the size of an atom. And actually just this month, I'm publishing, I published a method to being able to use this microscope to see the smallest physical singularity in existence, which is in a crystal. And it's about 1/10 the size of an atom. But I have other machines there. I have 2 scanning electron microscopes, and one of them is the most powerful in the world. It sees atoms on surfaces of materials. I got a few machines there. I'm interested in looking at time events too, but I collaborate on this other one, dynamic transmission, with INRS in Quebec. And then I have I collaborate with Karen Kavanagh and SFU on an ion microscope, and that one's coming along nicely. Unfortunately, my confocal scanning laser holography microscope, which can measure temperature, pressure, and composition in fluids three-dimensionally without disturbing the measurement, it doesn't exist anymore. It got destroyed about 1.5 years ago. But it's really targeting an International Space Station experiment. So I don't know if I'm going to have to resurrect this microscope, but it took 7 years to actually build. So I'm not enthusiastic. Anyway, I have a diffuse acoustic confocal medical imager, and that's why I'm a member of the biomedical research group here at UVIC. This microscope is now under, there's a UK company bringing it to market, and its specialty is that it can see diseased tissue like tumors. It can analyze whether the tumor is benign or carcinogenic or cancerous, and it can treat the tumor with a high intensity probe beam, and it can monitor the treatment process. So you can imagine with all those features how it needs to get out and be used and get out of my lab. So it's been so good, it can see details inside the body, such as where the egg is emitted from the ovaries and how it's picked up by the little fimbriated ends on the fallopian tube. So those things had never been seen before, and they get nicely seen by mine. Anyway, there is a software-defined sonar Earth Ocean Imager. This one is the youngest of the group, and there's definitely some possibilities of members of ISIC being interested in this one. I had 5 students work on it. It moved positively. It still needs a lot to do. The software-defined radio Earth atmosphere imager, I'm going to talk about that today. It's been around for over 10 years. It sees things that haven't been seen before and gets us to measure certain features of Earth disturbances, such as their power, energy, and where they occur. So that'll be part of it. So this is actually the star of the show these days. It's titanium dioxide. And what I do with it is titanium dioxide is well known for, it's paint. It's our white base on our paint. It's in our toothpaste. It's in food as filler. It's all over the place. We've been consuming it for 70 years. But as a catalyst, it's not very good because it requires ultraviolet light, and any kind of electron or hole generated, it recombines right away. And as you know, UV doesn't go through glass and it doesn't go through water. So its applications as a catalyst is extremely limited. To change that to absorb visible light, and which, as you know, goes through glass and it goes through water, I added just a little bit of iron, but I wasn't the first to try it. Many people have been trying it for about 25, 30 years, I read in publications, and it only usually had about 2 to 4% activation. So we made some up, stuck in the microscope, and we could see on the surface of the crystal this modelly looking stuff, which is a contamination layer. And it was actually the iron oxide, and it prevents the electrons and holes from reaching the surface so they can be used as a catalyst. When we clean those off and get the atomic planes going right to the surface of the crystals, you can see those here, the activation goes to 100%. And it's a massive hydroxyl radical generator. So it has these very special properties. I'm so impressed with it. I'm amazed at how efficient these crystals are at generating hydroxyl radicals, which can be used for all kinds of purposes. So this is what they look like. They're just a little powder. Their average size is 5 microns, so they aren't nanotechnology. The first thought of me when I created these things was to help clean wastewater. And we can see here, this is all the wastewater in our local region here being dumped out into the ocean. And what happens is that it creates all this algae blooms, red tides and stuff, and it's killing our shorelines, and it needs to stop. And it's there because we don't clean our water good enough, mainly the ammonia in it. But this really, we have to do better than what we've been doing, and the present state isn't good enough. So that was the initial motive of it. So over the years, I've learned how to activate these iron-doped titanium crystals with visible light. But if I go and clean out a pollutant of about 15 parts per million, which is 50% higher than normal wastewater treatment centers, and 20 times the volume of the reactor that's doing the cleaning, these days bioreactors are just about 1-to-1. But I found that using visible light to activate the crystals, this cleaning of this solution here of this pollutant, it takes hours. Our first success was 24 hours, but we got it down to about 9 or so. But then I found a way using electricity to stimulate the crystals to generate these hydroxyl radicals, and it just takes minutes. I'll show you this data. The activation methods are different. The visible light is photoelectric effect. This is with band gap theory. And then we have 3 chemicals actually, which we can mix with the crystals, and the cleaning just takes seconds. But ideally, we don't want to add anything. Electricity is clean. And so if we're going to clean things, it's best to not leave any residue behind, but except the byproducts that you want to see. So anyway, being able to generate the hydroxyl radicals with these crystals with electricity enables their activation in dark. We don't need oxygen, so hypoxia conditions are fine. The crystals aren't consumed in the cleaning process, so their lifetime is theoretically forever. And we can mix them in with water and spritz them onto a surface, and they keep the surface germ-free for about a month until the surface is re-cleaned. And so it has, lifetime is very long. And so we don't lose the crystals in the cleaning of the wastewater. We attach them to porous glass, and the bond is very good. You have a TiO2 bond with an SiO2 of the glass, and in between, they bond on the oxygen, so there's no mixing of the silicon titanium dioxide, so the crystal's properties don't change by this bonding process. And it looks like this. Here you can see some fiberglass cloth. You see all these little bumps on the surface. Those are the crystals. And where the target's hydroxyl radical, you can't get anything stronger. It has 2.8 oxygen potential. So this is really the target. So what we're testing the crystals on in the lab is methyl orange. It has a oxidation potential of 2.7. We also use phenol, has 2.8. Phenol just takes a little longer. But we find that these, when we test the crystals with ibuprofen, the ibuprofen decreases significantly. So, but we don't know what the oxidation potential is for ibuprofen, but we just know it works. And we're confident that it'll work with heavy metals, organic heavy metals. And the phenol actually is representative of the backbone of a lot of these forever type of chemicals in our water system now that are highly carcinogenic. So we think they'll be good with that. So the thing is, with this hydroxyl radical, the way we produce them is we just start with water and we dissociate it and we produce these hydroxyl ions, which then are going to react with an iron ion in the crystal. Well, actually so this iron ion will release, actually it'll capture the electron from the hydroxyl ion, producing the hydroxyl radical. And it does this very efficiently. So that's how the ionic current helps us in this. And so you can see here, if what we do is we put the crystals in between a anode and cathode, and the ion current flowing through from one electrode to another, it passes through a membrane with the crystals, and the current would actually like to pass through the crystals because it's less resistance than passing it through the water. And so on its way, it activates the crystals. And on one side, we generate a lot of hydroxyl radicals. On the other side, we produce a lot of superoxygen radicals. They aren't nearly as high in oxidation potential, but they contribute to the cleaning as well. But what we also generate here from the hydronium ions is a lot of hydrogen. So it's something we can use to help fuel this process here. Here's what you can see, the current prototype. Maybe it's prototype 20. I forget how many, but we start with a amount of pollutant in the water, which is easily to see. And you can see down here, it changes with time, and after about 20 minutes or so, it's completely cleared out. And so this is very rapid. If this was a bioreactor, it would take 24 hours, but also the power is really low. It's only 100 watts. And the other thing, it produces a lot of hydrogen bubbles, but the bubbles are so fine, they're like a mist. And we see some collecting on the surface of the tank, but actually inside, there's this mist where there's all these hydrogen bubbles. They're so small, you can barely see them. And it's because we have hydrophilic and hydrophobic surfaces inside the reactor that kind of promote this very fine hydrogen bubbles. And we want them to get into solution and not to stay on the electrodes, the cathode. And so we have some nice materials in there that do that. And also the reactor doesn't corrode. So all of that has been taken care of. Here we can see how we can look at the degradation of the methyl orange, which is representative of the total organic content. We can see how it increases as you increase the current passing through the water. So you really have control over how fast you want to clean and how much power you want to use. And so it lends a lot of flexibility. And I should mention that this reactor here is now being used, tested against commercial fish and shrimp ponds, as well as the wastewater coming from hospitals, which are extremely high in ammonia and pharmaceuticals. And it's doing well, so I hope this becomes its first applications widespread. This is the power used. We can see that we can actually, obviously with the increase in power, the degradation of the ibuprofen or the methyl orange increases. I'm not quite sure. We have to flesh out this a little further because it could actually rapidly rise and then saturate it off. I've seen that before. So I don't think it's a linear relationship here, but it's nice. We see that the thing is operating at low powers. And if we actually look at how this could be used in for cleaning wastewater now by the city and the sanitation and stuff like that, this is just a chart showing the recycling of the water and energy and stuff like that. So if we start with clean water from the lakes and rivers and ocean, and we use that with our food, we get the wastewater, the solids go off as fertilizer, but we sometimes call these crystals SteriClean crystals. We add electricity. The byproduct is water, carbon dioxide, and chemical fertilizers, but also a byproduct is hydrogen. The chemical fertilizers and CO2 are perfect for hydroponics And actually we found recently that duckweed is extremely good as a hydroponic for taking up the CO2, but also phytoplankton is very good. And then we can mix, the oxygen and hydrogen, produce the power to reduce the cost of cleaning the water. We get water coming out and it goes back clean, clean water goes to the ocean, lakes and rivers. So this is our ideal. This is what we want. Also the water and the organic fertilizers can be going to the farms and stuff, and we can produce food. So this is essentially the sustainability diagram. For cost for cleaning right now at 10 parts per million, cleaning 24 liters of methyl orange, we find that it is operating at 105 watts, and it cleans everything out in about 20 minutes. And so the cost is $0.003 for this. If we apply that to what we have here in Victoria with the new reactor, it's cleaning in its containers 10 million liters. And it has also the 10 ppm average pollutant concentration. If we are to use a reactor for this, it would cost $1,300 for the 10 million liters of cleaning. But the cost for the current actually was what I'm using at home, 0.09 cents or $0.09 per kilowatt hour. But Metro Vancouver, they're getting it for half that price. So really, for cleaning this much, and I'm sure Victoria is about the same, even though they won't tell me, that they're getting about, it would cost about $650 for 10 million liters of polluted water. And we could reduce that with using a fuel cell. So really, the way I look at it is that the wastewater is full of ingredients that are, you can make products out of. And so it has the organics, ammonia, fertilizer, all kinds of stuff in it. And so if we were to clean it out, we could clean it for free, and we would get fertilizer, food, fuel, and water. And all of these could be sold, and all I would have to do is make more than $650. And I think that's possible. So this is kind of in my thinking what would be for a business plan. So that's it for the using the crystals to clean water and other things. There's a plethora of uses for them, but this is where it's quite obvious any kind of collaboration with UVIC would be good, especially in this the power consumption and the use of hydrogen. Does anybody have a question or a comment?
Your previous slide, Rodney, where you had actually one more.
Yeah.
So your value proposition there, what's out of 10 million liters, how much product is there actually? So it's 10 parts per million.
Right. So we have to do those numbers. I'm sorry, I can't give them to you right now. I can show you where we're going in terms. Actually, I'm missing some slides here. I'm surprised. Oh no, I caught them all. So at this time, I really don't know how much it is. It has to be investigated, but we're thinking about it. Okay. This is thinking, right?
And the process you've described, is this, I'm trying to understand where these constituents are going. Like, is this a batch process and these materials accumulate on your crystals, so you eventually have to shut it down, or?
Oh, good question. So batch process is fine, that the reactor is fully scalable. It could actually clean in a pipe too. Every time I talk to a wastewater treatment person, their final comment to me is, can this thing clean the wastewater passing through a pipe? So if the pipe is long enough and gives us about 2 minutes, we can knock at least about 50% out of it, the organics. But you know, there's still quite a few unknowns here. Exactly what was your question again?
I'm just imagining what you've described. If you had a reactor like a pipe, where are these organics going? Like, are they accumulate on the surface of these crystals?
Right. So when the pollutant gets onto the surface of the crystal, that's when it meets a hydroxyl radical and gets oxidized. So having the pollutant have really good wettability on the surface of this fiberglass cloth, which holds the crystals. The surface of the glass fibers are just coated with the crystals. And so to get it to clean rapidly, we want the pollutant to touch the crystals. And so that's where the hydrophilicity actually is very important. So it touches the crystals and the pollutant oxidizes. So ammonia goes into the nitrates, the carbon-based ones go into carbon dioxide, so the crystals are self-cleaning, and you get a pollutant. They get a pollutant on themselves. They get activated, and they clean their surfaces of the pollutant. And this is how it works.
So coming out of the end of this pipe, you'd have essentially some CO2 gas, but you'd have other things in solution that would then require some sort of separation?
Yeah, actually, you can see here. So the wastewater comes in with all the organics and ammonia, the pharmaceuticals. It's treated with these crystals, and what comes out is water, carbon dioxide, and chemical fertilizers. So if we were to actually have the effluent go into a water system, it's going to pollute the water system, and that's not our goal. So what we do is, for our final cleaning, is put it into a reactor which has phytoplankton or hydroponics. And with that, one of my ex-students now has a company in Victoria called Industrial Phytoplankton. So he's looked at this, and it's the same stuff that he's using to grow his phytoplankton. And he makes a great reactor. So we can have the effluent from my reactor go to his reactor, and then we come out with really clean water. And also we get fertilizer and possibly some forms of food with the hydroponics. So is that?
Yeah, that explains it. That makes sense. Yeah.
I have a question on that. What about heavy metals in the fertilizers? Do you have any concerns about this? So I come from a wastewater treatment background as well, and with fertilizers, we're always worried about heavy metals and toxic metals. What about that?
Okay, so heavy metals, they're organic heavy metals are the problem. If these crystals will oxidize the organic heavy metal and change it into a metal oxide, which is inert. In terms of any kind of mercury or lead or something like that coming out of the ground, this will oxidize it and make it inert. So I think it will be effective against the heavy metals.
Okay. Can you also allude to the technical expertise of this unit process? When wanting to employ this at water and wastewater treatment facilities, there's a lot of these organizations are worried about the expertise that you're going to need to run such a process, or I guess sort of the consulting help that you may need to have this at your plant. Is this something that's feasible at many regional or city scale wastewater treatment facilities?
Well, I'm a professor, and I'm not, at a wastewater treatment facility. And so my job is to create the thing that can be used by others. And this is what this is about. I don't know about training people, but I believe this device is extremely easy to use. In fact, it's being used now. on the commercial fish ponds and hospital water. And all the people do is they take a sample of the wastewater, they put it into that bucket I showed you, and they turn it on, and it cleans out, and they take samples with time. So it's not difficult. It's just a matter of adjusting the current you want to pass through the reactor and how fast and how much power you want to use, those kinds of things. So it's not a difficult device.
That's good. And then that's quite important. I just say from a business standpoint, you know, to really get the adoption that you would want, you have to make it dummy proof in many ways, just so that they can take that leap of faith. But from an engineering standpoint, it's quite interesting.
Yeah, I agree with you entirely. It has to be dummy proof. And, you know, I send these reactors out to people and immediately they start taking them apart when they get it. And that they're showing me my device all taken apart, and they're tinkers. They love to see how things work. So they put it back and the thing's still working. And that's just part of the process of giving people these reactors to test in conditions that I don't have at the university. I have a lot of faith in it. I think it's, to me, it's proven itself over and over and over again. And I think it can do a lot of good. And it can be used in the ponds of agricultural ponds, mine tailing ponds, all kinds of things. So it has a lot of uses, far more than I have time or energy to actually support. But that's why I give it to people who have these interests, and they can try it out themselves.
So is there IP associated with this, Rodney? Is there something to do with the crystals, or?
Yeah, it's all protected. It has, the crystals has a patent already, and then I have about 10 surrounding patents.
Okay. Yeah, so it sounds to me like you're at this, you've got this sort of, I don't know if catalyst is the right word, but kind of like a catalyst that is highly effective, and you're now at the stage where you need to do process optimization. It's now it's kind of like a classic reactor problem where you have a surface area, pressure drop, a flow, a transport problem, basically.
Yeah.
So there needs to be some engineering.
That's right.
around that. Yeah. Okay. Interesting.
Yeah. So that's this. I hope you find my next one interesting. I just love it. So it's about characterizing Earth's atmosphere and ionosphere using radio waves. And so this one is about 10 years old, and it has now some really nice data. But if we use radio waves with about 1 to 5 megahertz frequency, then they reflect off Earth's ionization layers. And as you can imagine, those layers on the very outside of the Earth. And so it's Earth's largest sensor. And it's actually, you look at it and it moves, it's Earth's most sensitive sensor. So it's something that we should be looking at more closely. And when it actually consists of 4 layers. When the sun is shining, there's a DE, F1 and F2. Mostly I use the F2 layers here reflecting off that. But at night, only the F1 and F2 combine, so we can use that F layer. So the thing about it is there's all these waves on the surface, the bottom surface of the ionization layer, and they believe about 20% of those waves are created by solar or space events, but about 80% of them believe are created by meteorological events. And so Earth generated events. And they've known about these things for 100 years. They've been looking at these waves on the surface of the ionization layer, one transmitter and then one receiver. And that one receiver is like having 1 pixel in an image. And how much can you see with 1 pixel in an image? Not very much. So what I did, I came along and I made a camera and I started looking at these waves. And what's nice is that the waves have very high amplitudes. They're really strong and they hold a wealth of information, as I'll show you. So the thing is where it comes in with power and energy. If you have like a point source generating waves, then you get the wave height is the amplitude, but it's really a phase shift. So what my device generates is a phase image. I already told you I'm not interested in the intensity. You wouldn't see this wave with the intensity, but you can see it with the phase. And so the amplitude square is proportional to the power of whatever this thing is generating that wave, the frequency, the energy, and then you can have various wave vectors. If it's a point source, you can be looking at it from various points of view. If you have two cameras, one at the top left here, and then one on the bottom here, then you could pinpoint exactly where this wave is being generated. So that's what we do. Towards the end of the talk here, I collect waves from two different cameras, and I find out where they're coming from. So you can have any kind of wave generated. It could be a gravity wave or even an electromagnetic wave. And what's kind of interesting, you can have a fault when they move. All the atoms at the interface of the fault, they all break their atomic bond, and they generate electromagnetic radiation comes out. So we don't see it, but when a fault actually happens, when an earthquake actually happens, not only do we get a huge gravity wave, we get a huge electromagnetic pulse coming out. And they've seen that on the surface of the Earth's ionization layer. So we have the wave equation for what's coming out, and then it has to couple with the ionization layer. And then as it moves away to where maybe the camera is, you got a damping factor there. So the only thing that's unknown here is we can measure these everything except for the direction it's going, the K value. And that's why we have two cameras going at different angles, and we can pinpoint where it is, the disturbing event. This is our UVIC measurements taken a long time ago. But you can see, we can see the D, E, F1, and F2 layers here. We have a ground wave here as a reference. So this gave some confidence that we could actually reflect some radio waves off these ionization layers. They're too noisy to see any waves. So we went to the Dominion Radio Astrophysical Observatory, or DRAO, and we transmitted from the nearby town, Penticton. We bounced it off the ionization layer, and we set up this antenna arrays. And you can see what we're looking at here are these waves on the surface of the ionization layer. And what's very interesting is sometimes instead of having just a constant wave, which we see all the time, it has a constant amplitude, frequency, and direction. But we get these spikes coming in. And as you know, British Columbia suffers from about 300 earthquakes per day. But also this was taken in July when there was a lot of lightning. So we were seeing these spikes as well. We don't know where they're coming or going or anything like that, but eventually I think we'll get it sorted out. So we went to, that was Dominion Radio Astrophysical Observatory. And then I got a grant to go to New Mexico, University of New Mexico. They had this long wavelength arrays. They have two, LWA SV and LWA1. And they have, both of these have 256 by 256 randomly placed antenna. So it looks kind of like this, but so this is a phase image using those antenna, and you can even see the waves in here. And there's a very strong one that's going vertically in this case. If we Fourier transform this and get a Fourier image, you can see all these points here represent a wave, an amplitude and a frequency and a direction. Waves are passing on the surface of the ionization layer. There's a lot. So to start with, we picked waves that had 60 hertz frequency, and we looked at those. But this just shows you an example of the different types of waves that are there. There's a whole bunch. And so the Earth is being disturbed by many things. But so we just focused on this 60 hertz one to start with. And what we found was that we are transmitting from Santa Fe. and it was being picked up by LWA1 down here in the lower left corner, and also LWA-SV here. And the actual place, the patch on the ionization layer we're measuring is in between the transmitter and the receivers. And so we're right in the middle in here. And you can see here, these are the Fourier transforms of those phase images. We see that where the wave vectors are pointing, the direction the waves are going, we see that most of them are pointing in and around Albuquerque, which is the biggest consumer of power in New Mexico. And there's also some reactors, power reactors here. So the thing about this is what we measure for the power of these 60 hertz waves is that they have 3.9 watts. If we take it in terms of the surface area, it's just 0.0025 watts per meter squared. If we calculate the theoretical power losses from the local power generating stations, the transmission lines, and usage by Albuquerque, we get 3.5 watts. So it lends some credibility to what we're measuring and what we should be measuring. But that's just with the 60 hertz here. And then I'm not really concerned about this kind of capture of the losses due to the power generating stations because the solar index is 1,367 watts per meter squared. So it's so much higher than that of what we're measuring at 0.0025. It's almost 1,000,000 to 1. So I don't think the losses due to generating stations would be contributing too much to heating of the Earth. So that's where this, to me, this is what it tells me. Now, how much time do we have? We have, I've got, it's 11:44. For just a few minutes, I can show you how we can use this device to actually measure the temperature, pressure, and composition of the Earth's atmosphere. If you don't mind, I'll just show these last few slides because I think we have a bit of time.
Yep, let's do it.
So we take that Fourier image and we hide all those peaks all over the place using a low pass filter. And I would use the same thing with an ocean imager. Whoops, hang on. I have to unhide these. So as I showed you in that Fourier image, we had these peaks. Those represent the waves. We don't want to see the waves. And so we put in a low pass filter, which can either be a physical thing or it can be a digital thing. And when we do that, we get the low frequency waves, and ideally, we want a no frequency wave. We want a flat surface to bounce the radio wave off. And the goal is to measure the temperature, pressure, and composition of the Earth's atmosphere three-dimensionally. And so if we look at, and what we're really measuring is the refractive index of the atmosphere, and then we can, if we have enough equations, we can solve for the three unknowns. So this is Earth's refractive index as a function of altitude. At the very high altitudes, it's a steady state, stable region. Towards the surface of the Earth, it's very active. And we have the change in temperature, pressure, and composition happening all the time. It's really active and unstable. So what I do is I linearize this using standard logarithms. And you can see two exponentials here. It's the top one here is steady state, and the bottom one is the active region. And we have certain constants. One of them is the height limit, and it can be given to us. In fact, balloon data tells us where this occurs. Also, we need the refractive index on the surface of the Earth, and then all the constants can be determined. And then we have the refractive index as a function of temperature, pressure, and composition. If we bounce radio waves off the D, E, F1, and F2 ionization layers, it gives us four equations. and we only need to solve for 3. So perhaps if there's something in the air in terms of composition, either water vapor or aerosols or something like that, we might be able to squeeze a 4th out of it. So that's essentially how it works. The other thing so is there any questions about that? Because I want to talk about some collaborations if they're possible.
Why don't you keep going, Rodney, and then if we have time to circle back to questions, we can.
Okay. So there's an NSERC Alliance grant, and I was going to submit it at this time last year, but the pandemic hit, and it involves the Ocean Networks Canada, World Clean Crystals, my students' company, Industrial Phytoplankton, another one of my students' companies, Camtech, and I have quite a few university professors signed up on it from mechanical engineering and civil engineering. And I'd like to get UVIC also, if they would like to collaborate on this. So this is one that I'd like to see you consider. And what it involves is wastewater, cleaning of the wastewater and all the engineering that goes with that. And I have the attention of the wastewater treatment centers of Victoria, Saanich, the Capital Region District, and Metro Vancouver. Metro Vancouver, I've had a couple of grants with on this project. So this is one thing I'd like you to think about. The other is a CFI grant that's coming up, the next one. The government has already announced it's going to emphasize environmental research. And as you can see, this is environmental research. So I think it's a dead winner in terms of power and how necessary it is to understand and use for the environment. And so you can see that I think somewhere along the line, we could collaborate on these two. And just in conclusion, as Chris Hadfield recently stated in his book, Astronaut's Guide to Optimism, we did well during the last decade, and it's a new decade, so let's get at it and do well again. Okay?
Thanks, Rodney. Yeah, it's really interesting. I got to think more about this ionosphere aspect, and I'm trying to understand the, well, what is it you get from it that we don't measure now? And so I'm thinking pressure, temperature.
Well, right now we have balloons, and they go up once a day or twice a day, and they measure one point, and then they move and measure another point, and they're drifting across the sky, so it's not straight up, and it's different every time they send it up. So that's essentially, and to be able to see it with a radar sat, something like that, it doesn't have the capability. And the other thing is the measurement needs to be very local. If you start using radio waves that are transmitted too far away, there's too many unknowns. So to solve the unknowns, we measure everything locally. And then what is assumes to goes up is assumed to be the same coming down. So it halves the number of unknowns. And so this is why right now they aren't measuring the temperature, pressure, and composition of the Earth's atmosphere three-dimensionally. In LIDAR, they shine the laser up and it reflects off clouds and stuff like that. It actually doesn't penetrate the cloud. So as a result, they don't know what the composition of the clouds are. And there's ice, there's snow, there's rain, there's all this kind of stuff. So LIDAR is not able to do it either. So that's why this is a unique device. And it's just coming into life of its own.
I think the composition angle is, to me, seems really interesting. Would be a ton of people and companies and governments interested in the composition side for obviously tracking what's going on with industrial activities and emissions and things like that. So yeah, I'm gonna have to think more about that one. Going back to, though we are going to run out of time here, going back to the Hydroxyl Radical Reactor and that alliance. I'm sure you've already talked to people like Caetano and Heather Buckley. I feel like they've probably got some overlapping interests there. And yeah, I do think I see it being now at a stage where it's a reactor design problem, so transport phenomena. So, you know, there's some overlap for sure with some of the, you know, it's kind of like fuel cell problems in terms of transport. So yeah, I think there's some overlap in that one for sure. And
Great.
given that it's got the potential, you know, organic byproducts and hydrogen and things like that, yeah. So I'd be happy to talk to you about how you know how we can help out with the alliance.
Great. You know,